Hello everyone, my name is Alessandro Brigente and I'm a postdoctoral researcher at the University of Padua, in the Department of Mathematics. And today I'm going to talk about the worthiness of brute forcing cryptocurrency addresses. So cryptocurrencies are digital currencies that are stored on a distributed ledger. So this means that there are digital assets that user can exchange in a peer-to-peer-like network. So if the ledger is permissionless, it means that everyone gets access to the history of transactions, meaning that everyone gets to retrieve the information on how many Bitcoins, for instance, have been exchanged between what user and what other user. And furthermore, everyone has access to the balance owned by each public address. This means that if we're talking about the Bitcoin blockchain, it means that everyone gets access to the information on how many Bitcoins a specific public address owns. The nice thing about Bitcoins is that in the last years, they reached very high levels. This means that, for instance, if we're talking about dollars, Bitcoins, a single Bitcoin nowadays is worth thousands of dollars. So then our question was, might it be profitable for an attacker to invest resources, meaning energy resources, computational resources, to retrieve the private key of a Bitcoin address and get to withdraw, and therefore steal all the Bitcoins owned by the particular address, by a particular wallet? So this is the fundamental question we posed in this paper and for which we gave an answer. And I'm going to show you what the answer is. The first thing to notice is may it be worth it. So how is we are focusing about the Bitcoin in this paper. So in here we show how the Bitcoins are distributed over the different accounts. So on the left figure, we see how many addresses own a certain range of Bitcoin. So on the x-axis, we have, for instance, the first range is from 0 to 0.001. So this figure shows how many addresses own an amount of Bitcoin in this range. So we see that a large number of addresses own a small number of Bitcoins, but then there is still a significant number of addresses that own a large amount of Bitcoin. On the right figure, instead, we have on the x-axis the very same thing, so the range of Bitcoins owned by addresses. And on the y-axis, we have the total balance in Bitcoin. So this means, for instance, in the range 1 to 10, we have almost 2 multiplied by 10 to the power 6 total Bitcoins, which is worth a huge amount of dollars, of course. So this means that there are addresses that owns a huge amount of Bitcoins, and therefore it might be actually worth it to invest resources to steal just the currencies associated to a single address. So the next thing is, okay, but the attacker still needs a certain amount of time in order to crack the wallet of a certain user, no? So if the total amount of Bitcoins owned by a certain user rapidly changes over time, then it might not be worth it, no? Because when the attacker manages to retrieve the private key, maybe the user already moved that huge amount of Bitcoin. But in here we see the balance in Bitcoin and how it evolves in time for the 3 richest addresses at the time of writing of the paper. So in here we see that there's a positive trend. It means that not only the number of Bitcoins owned by a certain address do not increase, but they also increase. So it might be the case that when the attacker manages to retrieve the private key, it gets more than she or he expected. So this might seem that it's definitely worth it, no? So we can invest a certain amount of money to buy energy and buy resources to try and steal the Bitcoins in the richest address. So in order for delivering this attack, we need to understand how the private key of a Bitcoin address is generated, no? So what we publicly see is the public address, but the way to withdraw and to access to the Bitcoin owned by a certain balance is to get the private key. And the process from the private key to the public address is a series of cryptographic operations that the attacker needs to understand before delivering the attack. So this is how addresses are generated in Bitcoin. So the first thing is user subscription. The user needs to subscribe to the blockchain. It has its own address. No? So first thing is to generate a private and public key pair. And again, these are generated upon user subscription. So the first thing is to generate a random private key, 256 bits, and then transform it into a public key with the same length through elliptic curve digital signature algorithm. Then once we get the 256-bit public key, we transform it into something shorter. And in particular, we apply the hash 160, which is also known as double hash. And then we applied base 50 with the check encode to get something more readable by humans. And this is how we get the public address. So now what we need to do in order to deliver the attack is the reverse process. Now we cannot retrieve the private key from the public address, but what we can do is to generate random private keys and see whether these correspond to any of the public addresses that are currently on the Bitcoin blockchain. So this is our threat model. No? So we have the attacker that get access to the public information that is stored on the blockchain, meaning how many Bitcoins are owned by the different addresses and what are the public addresses. So again, we need to, the attacker needs to run the reverse process, starting from the public address. We said that is impossible to retrieve the private key, but on the other hand, it's possible to generate random private key and see whether these correspond to any known or publicly available address on the Bitcoin blockchain. So if we get, if the attacker gets to generate a public a Bitcoin address, it means that it was able to generate a private key that actually corresponds to one of the accounts in the Bitcoin blockchain, and therefore it means that the attacker has access to the Bitcoins associated to that address. In order to validate or to assess the performance of this attack, we compute the average reward. So the number of keys that the attacker is able to generate depends on an initial investment. This is due to the fact that generating private keys implies having computational power, and we pay computational power via electricity. So we assume that the attacker has an initial investment, a certain amount of money that the attacker is willing to spend to buy electricity and therefore generate private keys. So this means that the attacker gets to generate a fixed amount of private keys that depend again on the initial investment. Now the probability of success is equal to the probability of generating the private key. In this case, we consider the richest address. So the probability of success is the probability of generating a private key that corresponds, after all the needed operation, to the public address of the richest address. So we compute the average reward as the probability of success times the number of Bitcoins associated to the richest address times the conversion to US dollars, for instance, or the conversion from Bitcoins to US dollars. So here we see what is the average reward versus the initial investment of the attacker. In particular, in order to assess the worthiness of the brute force attack, we compare it with the mining process. Also, in the mining process, we have that the user, the miner, may want to spend an initial investment to buy hardware and to use electrical power and to eventually get a reward thanks to the mining process. And so in this figure, we see that the mining is way superior, attains way superior performance compared to the brute force attack. So indeed, we see that the average reward of a brute force attack, despite of the initial investment, which might be million, is still below 10 to minus 44, which is really low. We also compare the brute force attack with again with mining and with the scratch card. We select the scratch card because again, it's a system where you try to get easy money somehow. You have an initial investment, you need to buy the scratch card, and then eventually you get to win some money based on the combination of numbers that you are able to obtain. And although everybody knows that scratch card is not that much of a worth game, we still see in this figure that is the average reward that someone can obtain via scratch card is significantly higher compared to the brute force attack. So this means that brute forcing Bitcoin addresses is definitely not worth it. So the point that we showed in this paper is that although a certain number of users own a huge amount of Bitcoins and therefore own a huge amount of dollars, for instance, it's definitely not worth it to invest stakes in order to retrieve the private key and therefore steal the Bitcoins associated to a certain wallet. We assess this by comparing the brute force attack with other strategies, and we see that if someone wants to get somehow easy money from Bitcoin world, it's definitely worth it to invest in the mining process instead of investing in the attacking the Bitcoin cryptocurrency system. Thank you.